Good evening. As we gaze up at the night sky, the stars and constellations above us have fascinated humanity for millennia. Each twinkling light holds a story, a history, and a mystery waiting to be uncovered. Join me as we delve into mind-blowing facts about stars and constellations, a journey that will illuminate the wonders of our universe and perhaps even lull you into a peaceful sleep under their celestial canopy. 1. Sirius, often referred to as the Dog Star, stands as the brightest star visible in the night sky from Earth. Situated within the constellation Canis Major, it comprises the stars Sirius A, a main sequence star roughly twice the mass of the Sun and over 25 times more luminous, and Sirius B, a white dwarf companion. Sirius A is easily visible to the naked eye, emitting a bluish-white light. Conversely, Sirius B, discovered in 1862, requires telescopic observation due to its faintness. Sirius is located about 8.6 light-years away and has held significant cultural significance across various civilizations. Ancient Egyptians associated it with the goddess Isis and considered its heliacal rising to herald the annual flooding of the Nile, marking the beginning of their calendar year. In contrast, the Dogon people of Mali possess intricate knowledge of Sirius B, underscoring their advanced understanding of astronomy. 2. Betelgeuse, located within the constellation Orion, ranks as a red supergiant star near the culmination of its life cycle. It stands as one of the most sizable known stars, with an estimated diameter roughly 1,000 times greater than the Sun. Betelgeuse's luminosity fluctuates periodically, suggesting ongoing processes such as pulsations or significant mass loss. Positioned approximately 640 light-years away from Earth, Betelgeuse plays a prominent role within Orion's constellation, serving as one of the shoulders of the mythological hunter. Astronomers predict that Betelgeuse will eventually culminate in a supernova explosion, a transformative event anticipated to occur within the next 100,000 years. Upon its detonation, Betelgeuse is projected to briefly outshine the entire Milky Way galaxy, rendering it visible even during daylight hours. 3. The Pleiades, also known as the Seven Sisters, constitutes an open star cluster located within the Taurus constellation. It ranks among the nearest star clusters to Earth, featuring stars believed to be around 100 million years old. The cluster encompasses hundreds of stars, though only a select few are visible to the unaided eye under optimal conditions. The moniker Pleiades stems from Greek mythology, where the stars represent the seven daughters of Atlas and Pleione. The cluster's brightest stars possess a distinct blue hue due to their high temperatures and luminosity, standing out vividly against the dark expanse of space. The Pleiades hold significant cultural significance across various global cultures, appearing prominently in ancient mythologies and folklore spanning millennia. For neutron stars, relics of massive stars that have experienced supernova eruptions manifest as incredibly dense entities. These celestial bodies generally materialize following the gravitational collapse of massive stars, ensuing upon the depletion of their nuclear fuel reserves. Neutron stars exhibit such immense density that a solitary teaspoonful of neutron star substance would register a weight totaling billions of tons on Earth's surface. Comprised predominantly of tightly packed neutrons, these stars boast densities akin to atomic nuclei. Neutron stars are further distinguished by their rapid rotation and formidable magnetic fields. Certain neutron stars emit beams of radiation that traverse the cosmos akin to cosmic beacons, a phenomenon scientifically acknowledged as pulsars. The detection of pulsars during the 1960s proved instrumental in confirming the existence of neutron stars and corroborating pivotal hypotheses within the realm of astrophysics. 5. Alpha Centauri, the nearest star system to Earth, resides approximately 4.37 light-years away within the Centaurus constellation. This system consists of three stars, Alpha Centauri A and Alpha Centauri B, which form a binary pair, and Proxima Centauri, a red dwarf star situated slightly closer to Earth than its companions. Alpha Centauri and B orbit each other closely, with Proxima Centauri located at a greater distance from the binary pair. Proxima Centauri gained significant attention in recent years due to the discovery of Proxima b, an exoplanet within its habitable zone, making it a prime candidate for potential extraterrestrial life. Alpha Centauri holds particular interest among astronomers, representing a nearby celestial neighbor that could provide valuable insights into stellar dynamics and planetary formation beyond our solar system. 6. The Milky Way galaxy, our cosmic abode encompassing the solar system, boasts a staggering population of over 100 billion stars. Structurally categorized as a barred spiral galaxy, the Milky Way features a prominent central bulge encircled by several spiral arms, including the Orion arm where the Sun and Earth reside. Spanning a diameter of approximately 100,000 light-years, the galaxy is replete with interstellar matter and a diverse array of stellar phenomena, from star formation regions to expansive nebulae and globular clusters. The Milky Way serves as a fundamental focal point for astronomical study, offering a unique vantage point to investigate the broader mechanisms underpinning galaxy evolution and the cosmic distribution of stellar populations. 7. Red giants represent a class of stars in the latter stages of their evolutionary journey, characterized by their substantial size and reddish hue. These stars originate from main sequence stars like our Sun, which expand significantly as they deplete their core hydrogen fuel reserves. Red giants achieve vast dimensions, with some swelling to hundreds of times the Sun's diameter, albeit with a lower surface temperature relative to their earlier stellar phases. The transformation into a red giant heralds the penultimate phase of a star's life cycle before it ultimately sheds its outer layers, yielding a remnant core known as a white dwarf. This evolutionary progression underscores the dynamism inherent to stellar life cycles, illuminating the intricacies of stellar evolution and the diversity of stellar phenomena observable across the cosmos. 8. White dwarfs represent the residual cores of stars similar to our Sun following their progression through stellar evolution. These compact stellar remnants, composed primarily of electron-degenerate matter, retain a high temperature upon formation, gradually cooling over billions of years. White dwarfs derive their name from their luminosity, which dims considerably compared to their earlier stellar phases. With masses comparable to that of the Sun but compressed to dimensions roughly the size of Earth, white dwarfs exemplify the final evolutionary stage for stars of moderate mass. Their existence serves as a testament to the cyclical nature of stellar phenomena, marking the culmination of stellar fusion and the transition into cosmic relics that contribute to the enrichment of interstellar environments. 9. The North Star, known as Polaris, holds a special place in celestial navigation due to its close proximity to the North Celestial Pole. Positioned within the constellation Ursa Minor, Polaris stands almost directly above Earth's northern axis, rendering it almost stationary in the night sky as viewed from the northern hemisphere. This unique celestial positioning has made Polaris a reliable reference point for navigators and astronomers alike throughout history. Ancient civilizations, including the Greeks and Romans, utilized Polaris to orient themselves and navigate across vast distances, aiding in exploration, trade, and cultural exchange. Its steady presence amidst the rotating canopy of stars has ensured its enduring significance as a guiding beacon in both terrestrial and astronomical realms. 10. Globular clusters constitute dense, spherical collections of stars that orbit galactic centers within the halos of galaxies. These clusters typically contain tens of thousands to millions of stars tightly bound together by gravitational forces, forming some of the oldest known stellar populations in the universe. Globular clusters exhibit distinct characteristics, including a central concentration of stars, a spherical shape, and a lack of interstellar gas and dust. Their ancient age, estimated to range from 10 billion to over 13 billion years, predates the formation of most galaxies, offering invaluable insights into early stellar evolution and the dynamics of galactic assembly. Astronomical observations of globular clusters provide a window into the primordial conditions of the universe and the enduring endurance of stellar communities across cosmic epochs. 11. Supernovae stand as cataclysmic stellar explosions that occur during the final stages of a massive star's life cycle, marking the dramatic conclusion of its nuclear fusion processes. These powerful events unleash an immense burst of energy, temporarily outshining entire galaxies and briefly rivaling the luminosity of billions of stars combined. Supernovae play a pivotal role in cosmic evolution by dispersing heavy elements forged within stellar cores throughout interstellar space, enriching subsequent generations of stars and planetary systems. Their transient brilliance serves as a cosmic crucible for the synthesis of elements crucial for the emergence of life, highlighting the profound impact of stellar phenomena on the dynamic evolution of galaxies and the cosmic landscape. 12. The Summer Triangle represents an asterism comprising 3 bright stars visible in the summer skies of the Northern Hemisphere. Formed by the stars Vega in the constellation Lyra, Deneb in Cygnus, and Altair in Aquila, the Summer Triangle stands out prominently against the backdrop of the night sky. This celestial formation holds cultural significance across diverse civilizations, serving as a navigational aid, seasonal marker, and inspiration for mythological narratives. The Summer Triangle's striking configuration facilitates celestial observation and scientific inquiry, offering astronomers and stargazers a captivating window into the vast expanse of the cosmos and the interconnectedness of stellar phenomena across spatial and temporal scales. 13. Sagittarius *SGR anchors the heart of our Milky Way galaxy as a supermassive black hole, shrouded within the dense star fields of the constellation Sagittarius. This enigmatic cosmic entity boasts a gravitational influence equivalent to about 4 million times the mass of our Sun, yet it occupies a remarkably compact space at the galactic center, spanning just a fraction of a light-year in diameter. SGR* stands as a testament to the profound interplay between gravity and astrophysical phenomena, drawing in surrounding gas and stars while emitting minimal detectable radiation itself. Despite its elusive nature, SGR* holds pivotal significance in astronomical research, serving as a laboratory for testing theories of general relativity and exploring the intricate dynamics of galactic evolution over cosmic timescales. Its central role within the Milky Way underscores the profound influence of supermassive black holes in shaping the structural and evolutionary trajectories of galaxies across the universe. 14. Cepheid variables are a class of pulsating stars whose brightness fluctuates predictably over time. These stars serve as crucial cosmic yardsticks, allowing astronomers to gauge vast distances within the universe with remarkable accuracy. The pulsation period of Cepheid variables correlates directly with their intrinsic luminosity. The longer the period, the greater their luminosity. This relationship, known as the period luminosity relationship, was first established by astronomer Henrietta Swan-Leavitt in the early 20th century while studying Cepheids in the Small Magellanic Cloud. By observing Cepheids in distant galaxies, astronomers can determine their distances based on the comparison between their observed brightness and their known luminosity from the period luminosity relationship. This method has proven invaluable in measuring cosmic distances and calibrating the cosmic distance ladder, a sequence of methods used to determine distances in the universe, ultimately shaping our understanding of the vast cosmic landscape and the fundamental structure of the cosmos. 15. The Summer Triangle is a prominent asterism formed by the stars Vega, Deneb, and Altair, visible in the Northern Hemisphere during the summer months. Each star belongs to a different constellation: Vega in Lyra, Deneb in Cygnus, and Altair in Aquila. Vega, the brightest star in the Summer Triangle, is relatively close to us at about 25 light-years away and serves as a standard reference point in astrophysics. Deneb, one of the most luminous stars known, lies approximately 2,600 light-years from Earth and marks the tail of the Swan in Cygnus. Altair, located about 17 light-years away, is notable for its rapid rotation, spinning so fast that it bulges slightly at the equator. Together, these stars form a striking geometric pattern that has fascinated stargazers and astronomers alike throughout history, serving as a beacon for navigation and a canvas for mythological tales across different cultures. 16. Andromeda, also known as Messier 31 M31, is a majestic spiral galaxy located approximately 2.5 million light-years away from Earth, making it the nearest spiral galaxy to the Milky Way. It spans a vast distance of about 220,000 light-years across and contains over 1 trillion stars, outshining our own galaxy in sheer size and luminosity. Andromeda is visible to the naked eye under dark skies and appears as a faint, elongated patch of light in the constellation Andromeda. This galaxy holds significant scientific interest as a cosmic laboratory for studying galaxy formation, structure, and evolution. In approximately 4.5 billion years, the Milky Way and Andromeda are expected to collide and merge, reshaping both galaxies and providing a glimpse into the future evolution of our cosmic neighborhood. 17. Circumpolar stars are stars that appear to orbit the celestial poles without ever setting below the horizon as seen from a specific location on Earth. The visibility of circumpolar stars depends on the observer's latitude. Stars near the North Celestial Pole are circumpolar for observers in the Northern Hemisphere, while stars near the South Celestial Pole are circumpolar for observers in the Southern Hemisphere. The rotation of Earth on its axis causes this phenomenon, with circumpolar stars appearing to move in a circular path around the pole. This constant visibility makes circumpolar stars useful for navigation and timekeeping throughout human history, offering a fixed reference point against the backdrop of the night sky. 18. The Hertzsprung-Russell diagram, named after astronomers Ejnar Hertzsprung and Henry Norris Russell, is a fundamental tool in astrophysics used to classify stars based on their luminosity, spectral type, temperature, and evolutionary stage. This diagram plots stars' luminosity brightness against their surface temperature, color, or spectral type, revealing distinct groupings such as main sequence stars like our Sun, giants, supergiants, white dwarfs, and more. It provides insights into stellar evolution, illustrating how stars progress through different stages based on their mass and composition. The Hertzsprung-Russell diagram remains crucial for astronomers to study the life cycles of stars, understand stellar populations within galaxies, and predict the future evolution of our Sun and other stars. 19. The Crab Nebula, catalogued as Messier 1 M1, is a supernova remnant located in the constellation Taurus. It formed after a massive star exploded in a supernova event observed by Chinese astronomers in the year 1054 AD. The Crab Nebula spans about 11 light-years across and is one of the most studied astronomical objects due to its historical significance and proximity to Earth, approximately 6,500 light-years away. At its center lies a pulsar, a rapidly spinning neutron star that emits beams of radiation like a cosmic lighthouse. The Crab Nebula's intricate structure and energetic phenomena provide valuable insights into supernova explosions, neutron stars, and the dynamics of interstellar material in our galaxy. 20. The zodiacal constellations, commonly known as the 12 signs of the zodiac, are a set of constellations that lie along the ecliptic, the apparent path of the sun across the sky throughout the year. These constellations have been used since ancient times to divide the sun's annual journey into 12 equal parts, each corresponding to 1 month of the year. The 12 zodiac constellations include Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpius, Sagittarius, Capricornus, Aquarius, and Pisces. Despite their astrological associations, these constellations serve as a useful reference for astronomers to locate celestial objects and track the movement of planets and other bodies within our solar system. 21. The Great Red Spot (GRS) is a massive storm located in Jupiter's atmosphere, visible as a persistent anticyclonic storm system larger than Earth. It has been observed for at least 400 years and possibly longer, making it one of the most long-lived and recognizable features in the solar system. The GRS rotates counterclockwise with a period of about 6 Earth days, generating winds that exceed 400 kilometers per hour to 150 miles per hour and creating a distinctive reddish hue due to complex chemical reactions in Jupiter's atmosphere. Studying the Great Red Spot provides valuable insights into planetary atmospheres, weather patterns, and the dynamics of gas giant planets beyond Earth's atmosphere.
22. The Oort cloud is a theoretical spherical shell of icy objects that surrounds our solar system, extending far beyond the orbits of Neptune and Pluto. Named after Dutch astronomer Jan Oort, who hypothesized its existence in 1950. The Oort cloud is believed to be the source of long-period comets, those with orbital periods exceeding 200 years. These comets are thought to originate from the outer reaches of the Oort cloud, where they are occasionally perturbed by passing stars or gravitational interactions within the Milky Way galaxy, sending them on trajectories that bring them closer to the Sun. Studying comets originating from the Oort cloud provides valuable insights into the composition of our early solar system and the dynamics of icy bodies in the outer reaches of our cosmic neighborhood. 23. The Horsehead Nebula Barnard 33 is a dark nebula located in the constellation Orion, positioned just south of the star Alnidak, the easternmost star in Orion's belt. It is a striking example of a dark nebula, appearing as a silhouette against the bright emission nebula IC 434. The distinctive shape of the Horsehead Nebula resembles a horse's head when viewed from Earth, thanks to the interplay of dark, dust and gas obscuring the light from the background nebula. The Horsehead Nebula is a site of ongoing star formation, with young stars embedded within its dense clouds of gas and dust. It serves as a captivating target for both amateur and professional astronomers, offering insights into the processes of stellar birth and the formation of planetary systems within our galaxy. 24. The Great Attractor is a gravitational anomaly located in the constellation Centaurus that exerts a strong gravitational pull on the Milky Way and other nearby galaxies. Discovered in the 1970s, this mysterious region of space lies beyond the Milky Way's galactic center and is thought to be a massive concentration of dark matter in galaxies. The Great Attractor's gravitational influence redirects the motion of our galaxy and countless others towards it, affecting the large-scale structure of the universe on cosmic scales. Despite its profound influence on the cosmos, the exact nature and composition of the Great Attractor remain topics of ongoing research and debate among astronomers.
25. The cosmic microwave background CMB radiation is the afterglow of the Big Bang, permeating the entire universe with a nearly uniform temperature of about 2.7 Kelvin. 270.45 degrees Celsius or minus 454.81 degrees Fahrenheit. Discovered accidentally in 1965 by Arnaud Penzias and Robert Wilson, the CMB radiation provides crucial evidence for the Big Bang Theory, offering a snapshot of the universe when it was only 380,000 years old. This radiation is the oldest light in the universe, originating from the time when atoms first formed and photons were able to travel freely. Studying the CMB allows astronomers to probe the early universe, map its structure, and uncover key insights into the origins, evolution, and fate of our cosmos. 26. Pulsars are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation along their magnetic poles. These beams are observed as regular pulses of radiation that can be detected from Earth as the star rotates, hence the name pulsar. Pulsars are remnants of massive stars that have undergone supernova explosions, leaving behind incredibly dense cores composed primarily of neutrons. The discovery of pulsars in 1967 by Jocelyn Bell Burnell and Antony Hewish revolutionized astrophysics, confirming the existence of neutron stars and providing strong evidence for the existence of gravitational waves. Pulsars continue to be studied extensively to explore fundamental physics, test theories of gravity, and probe the properties of extreme states of matter under immense gravitational pressures. 27. The Veil Nebula is a supernova remnant located in the constellation Cygnus, resulting from a massive star that exploded approximately 8,000 years ago. It is one of the most spectacular and intricate nebulae in the night sky, spanning a vast area across space and appearing as delicate wisps of glowing gas and dust. The Veil Nebula is divided into several sections, including the Eastern Veil NGC 6992-6995, and the Western Veil NGC 6960, each displaying intricate filamentary structures illuminated by the shockwaves from the supernova explosion. Studying the Veil Nebula provides valuable insights into the dynamics of supernova remnants, the recycling of stellar material, and the enrichment of interstellar space with heavy elements essential for the formation of new stars and planetary systems. 28. The Tunguska event was a mysterious explosion that occurred on June 30, 1908, near the Podkamennaya Tunguska River in Siberia, Russia. The event is believed to have been caused by the airburst of a small asteroid or comet fragment entering Earth's atmosphere and exploding in midair. The blast flattened an estimated 80 million trees over an area of about 2,150 square kilometers, 830 square miles, but fortunately, no human casualties were reported due to the remote location of the impact. The Tunguska event remains one of the most significant cosmic impact events in recorded history, sparking scientific interest in asteroid and comet threats to Earth and underscoring the importance of monitoring near-Earth objects (NEOs) for planetary defense and understanding the dynamics of our solar system. 29. The Drake equation is a probabilistic formula used to estimate the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. Formulated by astronomer Frank Drake in 1961, the equation considers factors such as the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction of planets where life evolves, the fraction of life-bearing planets where intelligent life evolves, the fraction of intelligent civilizations that develop technology detectable from space, and the length of time such civilizations release detectable signals into space. While the values for many of these factors remain uncertain, the Drake equation serves as a framework for discussing the likelihood of extraterrestrial intelligence and stimulating scientific inquiry into the search for life beyond Earth. 30. The International Astronomical Union (IAU) is the official body responsible for assigning names and designations to celestial objects and phenomena. Founded in 1919, the IAU facilitates international cooperation in astronomy and promotes the advancement of the science through various initiatives, including the standardization of astronomical nomenclature, the definition of fundamental astronomical constants, and the organization of scientific conferences and symposia. The IAU is perhaps best known for its role in demoting Pluto from planet status to that of a dwarf planet in 2006, a decision that sparked widespread debate and discussion among astronomers and the public alike. 31. The James Webb Space Telescope JWST is a highly anticipated space observatory scheduled for launch by NASA, ESA European Space Agency, and CSA Canadian Space Agency. Set to succeed the Hubble Space Telescope, JWST is designed to operate primarily in the infrared region of the electromagnetic spectrum and promises to revolutionize our understanding of the early universe, star formation, exoplanets, and other astronomical phenomena. JWST features a large segmented mirror, advanced instruments, and a sun shield to protect it from solar radiation, enabling it to observe faint and distant objects with unprecedented clarity and sensitivity. Once operational, JWST is expected to unveil new discoveries and insights into the cosmos, pushing the boundaries of human knowledge in astronomy and astrophysics. 32. The Kuiper Belt is a region of the solar system extending beyond the orbit of Neptune, populated by countless icy bodies and dwarf planets, including Pluto. Named after Dutch-American astronomer Gerard Kuiper, who predicted its existence in 1951. The Kuiper Belt is analogous to the asteroid belt but composed mainly of frozen volatiles such as methane, ammonia, and water ice. This region is thought to be a reservoir of primitive remnants from the early solar system, offering insights into planetary formation and the conditions that prevailed during the solar system's infancy. The discovery of numerous Kuiper Belt objects has expanded our understanding of the outer solar system and continues to inform studies of planetary dynamics and evolution. 33. The Hubble Space Telescope (HST) is a space observatory launched into low Earth orbit by NASA in 1990. Named after astronomer Edwin Hubble, Hubble's deployment marked a significant milestone in astronomy, providing unprecedented views of distant galaxies, nebulae, and other celestial objects across various wavelengths of light. Equipped with a large primary mirror and a suite of advanced instruments, Hubble has contributed immensely to our understanding of cosmology, galactic evolution, stellar dynamics, and the search for exoplanets. Its observations have yielded iconic images that have captivated the public and revolutionized our perception of the universe, paving the way for subsequent space observatories and shaping modern astrophysical research. 34. The Fermi paradox poses the question of why, given the vast number of stars in the Milky Way galaxy and the potential for habitable planets, we have not yet detected any signs of extraterrestrial civilizations. Named after physicist Enrico Fermi, who famously raised the issue in the 1950s, the paradox highlights the apparent contradiction between the high probability of extraterrestrial life and the lack of observable evidence for such civilizations. Various proposed solutions to the Fermi paradox range from technological limitations in detecting extraterrestrial signals to hypothetical explanations involving the rarity of intelligent life or potential existential threats that civilizations may face. Addressing the Fermi paradox remains a key focus of astrobiology and SETI search for extraterrestrial intelligence research, stimulating ongoing efforts to explore and understand the potential prevalence of life beyond Earth. 35. Exoplanets, or extrasolar planets, are planets that orbit stars other than our Sun. The discovery of exoplanets has expanded our understanding of planetary systems and the potential for habitable worlds beyond our solar system. The first confirmed detection of an exoplanet orbiting a main sequence star occurred in 1992, marking a breakthrough in astronomy. Since then, advancements in observational techniques such as the transit method and radial velocity method have enabled astronomers to detect thousands of exoplanets. These discoveries include a diverse array of planetary types, ranging from gas giants larger than Jupiter to rocky planets smaller than Earth, orbiting stars across different regions of the Milky Way galaxy. Studying exoplanets offers valuable insights into planetary formation, evolution, and the conditions necessary to support life, fueling ongoing research into the potential habitability of distant worlds. 36. Dark matter constitutes approximately 27% of the total mass energy content of the universe, making it one of the most abundant forms of matter in existence. Despite its prevalence, dark matter remains elusive and undetectable through direct observation due to its apparent lack of interaction with the electromagnetic radiation. Its existence is inferred indirectly from its gravitational effects on visible matter, galaxies, and the large-scale structure of the universe. Dark matter is hypothesized to be a non-baryonic substance that interacts primarily through gravity, contributing significantly to the formation and evolution of cosmic structures. Understanding the nature of dark matter is a major goal in modern astrophysics and particle physics. with ongoing efforts focused on detecting dark matter particles, exploring alternative theories of gravity, and probing its role in shaping the cosmic landscape on both galactic and cosmological scales. 37. Cosmic inflation is a theoretical concept in cosmology that proposes a rapid exponential expansion of the universe in the first fraction of a second after the Big Bang. Proposed in the 1980s to address certain problems in the Big Bang theory, inflationary models suggest that the universe underwent a phase of accelerated expansion driven by a hypothetical scalar field called the inflaton. This rapid expansion would have smoothed out irregularities in the early universe, providing a mechanism for the uniformity observed in the cosmic microwave background radiation and the large-scale structure of the universe today. Although direct evidence for cosmic inflation remains elusive, observations of the cosmic microwave background and large-scale structure provide strong support for its theoretical framework, making it a key component of modern cosmological models. 38. Neutron stars are incredibly dense remnants of massive stars that have undergone supernova explosions, leaving behind a core composed almost entirely of neutrons. These exotic stellar objects pack more mass than the Sun into a sphere roughly the size of a city, resulting in densities comparable to atomic nuclei. Neutron stars exhibit extraordinary physical properties, including intense gravitational fields, rapid rotation rates, and powerful magnetic fields. Some neutron stars, known as pulsars, emit beams of electromagnetic radiation that sweep across space like cosmic lighthouses, detectable as regular pulses due to their rotational spin. Studying neutron stars provides insights into extreme states of matter, the physics of nuclear interactions under extreme conditions, and the behavior of matter in the presence of intense gravitational forces. 39. The cosmic web is a large-scale structure of the universe composed of interconnected filaments of galaxies and voids that span vast distances across space. This intricate network forms through gravitational attraction, with galaxies and galaxy clusters congregating along dense filamentary structures while leaving expansive voids relatively devoid of galaxies. The cosmic web represents the large-scale distribution of matter in the universe and serves as a framework for understanding cosmic evolution, galaxy formation, and the growth of structures over cosmic time. Observational surveys mapping the cosmic web provide crucial insights into the underlying cosmic structure, the nature of dark matter and dark energy, and the processes shaping the evolution of galaxies and galaxy clusters within the cosmic landscape. 40. Gravitational lensing is a phenomenon predicted by Albert Einstein's general theory of relativity, where the gravitational field of a massive object, such as a galaxy or cluster of galaxies, bends and distorts light from more distant objects behind it. This effect can produce multiple images or distorted, magnified views of background galaxies, stars, or quasars, providing astronomers with a powerful tool to study both the foreground lensing object and the background source. Strong gravitational lensing can create Einstein rings, arcs, and multiple images of the same source, offering insights into the distribution of dark matter within the lensing object and enabling detailed investigations of distant galaxies and their properties. 41. The Fermi Gamma Ray Space Telescope, launched by NASA in 2008, is a space observatory designed to study gamma ray emissions from celestial sources, including pulsars, supernova remnants, active galactic nuclei, and gamma ray bursts. Named after physicist Enrico Fermi, the Fermi Gamma Ray Space Telescope has revolutionized our understanding of high-energy astrophysical processes and the most extreme environments in the universe. Its observations have provided crucial insights into the acceleration of cosmic rays, the formation and evolution of black holes, and the nature of gamma ray bursts, shedding light on fundamental physics principles and cosmic phenomena that cannot be observed through other wavelengths of light. 42. The Event Horizon Telescope (EHT) is a global network of radio telescopes linked together to form an Earth-sized virtual telescope capable of capturing images of black holes. In April 2019, the EHT collaboration unveiled the first-ever image of a black hole's event horizon located at the center of the galaxy M87. This historic achievement marked a significant milestone in astrophysics, confirming the existence of black holes and providing direct observational evidence for the predictions of general relativity. The EHT continues to observe other black holes, including Sagittarius A* at the center of our Milky Way galaxy, with the aim of furthering our understanding of these enigmatic cosmic objects and their role in shaping the dynamics of galaxies and the universe at large. 43. The Drake equation, formulated by astronomer Frank Drake in 1961, aims to estimate the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. It considers factors such as the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, and other variables to provide a framework for discussing the likelihood of intelligent life beyond Earth. While the values for many of these factors remain uncertain, the Drake equation remains a foundational tool in astrobiology and the search for extraterrestrial intelligence (SETI), stimulating ongoing research and speculation about our place in the cosmos and the potential for contact with other civilizations. 44. The Andromeda Galaxy, also known as Messier 31 M31, is the nearest spiral galaxy to the Milky Way, located approximately 2.5 million light-years away in the constellation Andromeda. Spanning about 220,000 light-years across, Andromeda is slightly larger than our own galaxy and contains over 1 trillion stars. Astronomical observations indicate that Andromeda and the Milky Way are on a collision course, expected to merge in approximately 4.5 billion years due to their mutual gravitational attraction. This cosmic event will reshape both galaxies and provide insights into galaxy formation, stellar evolution, and the future of our local group of galaxies. 45. The Sun is a middle-aged star located at the center of our solar system, composed mainly of hydrogen and helium gas undergoing nuclear fusion to produce energy. It is approximately 4.6 billion years old and has an expected remaining lifespan of about 5 billion years before it transitions into a red giant phase, swelling in size and engulfing Mercury and Venus before shedding its outer layers to form a planetary nebula. Ultimately, the Sun will collapse into a white dwarf, gradually cooling over trillions of years. The study of the Sun, known as heliophysics, is essential for understanding solar activity, space weather, and its influence on Earth's climate and technological infrastructure. 46. Cosmic rays are high-energy particles, mostly protons and atomic nuclei that originate from outer space and travel at nearly the speed of light. They can reach Earth's atmosphere from various sources, including supernovae explosions, active galactic nuclei, and other astrophysical processes. Upon entering the atmosphere, cosmic rays collide with their molecules, initiating cascades of secondary particles known as extensive air showers. Studying cosmic rays provides valuable insights into astrophysical phenomena, particle physics, and the effects of high-energy radiation on Earth's atmosphere and space-based technologies. 47. The interstellar medium ISM is the vast expanse of matter and radiation that fills the space between stars within a galaxy. It consists of gas, mostly hydrogen and helium, dust grains, cosmic rays, and magnetic fields permeating the entire galaxy and playing a crucial role in stellar formation, evolution, and the recycling of material between stars. The ISM is divided into several components, including molecular clouds where stars are born, ionized regions energized by hot stars, and diffuse regions containing a mix of gas and dust. Observing the ISM across different wavelengths of light provides astronomers with essential clues about the conditions and processes shaping galaxies and their evolution over cosmic timescales. 48. The heliosphere is a vast region of space dominated by the Sun's influence, extending far beyond the orbit of Pluto and encompassing the solar wind, magnetic field, and solar energetic particles. It acts as a protective bubble that shields the solar system from most of the harmful cosmic rays originating outside our solar system. The boundary of the heliosphere, known as the heliopause, marks the point where the solar wind meets the interstellar medium, transitioning from a region dominated by the Sun's influence to the influence of the local interstellar environment. NASA's Voyager spacecraft have provided valuable data on the structure and dynamics of the heliosphere as they continue their journey into interstellar space, offering insights into the interaction between our Sun and the wider galaxy. 49. Quasars, short for quasi-stellar radio sources, are extremely luminous and energetic objects located at the centers of some galaxies. They are powered by supermassive black holes millions to billions of times more massive than our Sun. Quasars emit enormous amounts of radiation across the electromagnetic spectrum, from radio waves to gamma rays, making them visible over vast cosmic distances. The intense radiation from quasars is thought to originate from the accretion disk of material swirling around the supermassive black hole, heating up and emitting light as it falls toward the event horizon. Studying quasars provides insights into galaxy evolution, the growth of supermassive black holes, and the energetic processes occurring in the early universe. 50. Cosmic microwave background CMB polarization refers to the pattern of polarization imprinted on the CMB radiation, which is the afterglow of the Big Bang. Polarization in the CMB provides valuable information about the early universe's conditions and processes, such as inflationary gravitational waves, the ionization history of the universe, and the distribution of dark matter. Measurements of CMB polarization are conducted by sensitive instruments deployed on ground-based telescopes and space observatories, allowing astronomers to study the universe's fundamental properties and test theories about its origins and evolution. 51. The Local Group is a small cluster of galaxies that includes the Milky Way, Andromeda Galaxy M31, and over 50 smaller galaxies bound together by their mutual gravitational attraction. The Local Group is part of a larger cosmic structure known as the Virgo supercluster, containing thousands of galaxies within a vast cosmic web. Studying the Local Group provides insights into galaxy formation, interactions between galaxies, and the dynamics of cosmic structures on scales ranging from individual galaxies to clusters and superclusters of galaxies. The proximity of galaxies within the Local Group allows astronomers to observe and study their properties in detail, offering clues about the broader processes shaping the universe's cosmic architecture. 52. Active galactic nuclei AGNS are regions at the centers of galaxies characterized by intense emissions across the electromagnetic spectrum, from radio waves to gamma rays. AGNS are powered by accretion disks surrounding supermassive black holes, with material swirling into these black holes releasing enormous amounts of energy. Different types of AGNS include quasars, blazars, and Seyfert galaxies, each exhibiting unique characteristics depending on the orientation of the accretion disk and the presence of relativistic jets. AGNS play a crucial role in galaxy evolution and are considered key drivers of the observed correlations between the masses of supermassive black holes and the properties of their host galaxies. 53. Gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. Predicted by Albert Einstein's general theory of relativity in 1915, gravitational waves were directly detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory LIGO. These detections confirmed Einstein's theory and opened a new era of gravitational wave astronomy, allowing scientists to study cataclysmic events in the universe that emit gravitational waves. Gravitational wave astronomy provides insights into the nature of compact objects, tests of fundamental physics, and investigations into the cosmic history of mergers and collisions that shape the universe's structure. 54. Supermassive black holes reside at the centers of most galaxies, including our Milky Way, and can have masses ranging from millions to billions of times that of the Sun. These black holes play a crucial role in galaxy evolution, influencing the growth and dynamics of their host galaxies through processes such as accretion of gas and stars, feedback mechanisms that regulate star formation, and the generation of powerful jets and outflows. Observations of supermassive black holes at various cosmic epochs provide insights into their formation mechanisms, growth rates, and interactions with their galactic environments, shedding light on the coevolution of galaxies and their central black holes throughout cosmic history. 55. The Hubble constant, denoted as h_0, is a fundamental constant in cosmology that describes the rate at which the universe is expanding at the present time. It quantifies the relationship between the distance to galaxies and the velocity at which they are moving away from us due to the expansion of space. Determining the precise value of h_0 is crucial for understanding the age, size, and fate of the universe. Current measurements of h_0 have sparked debate and research due to discrepancies between different observational methods, highlighting ongoing efforts to refine our understanding of cosmic expansion and the underlying physics driving it. 56. Gamma-ray bursts (GRBS) are brief, intense bursts of gamma-ray radiation originating from distant galaxies, marking some of the most energetic events in the universe. GRBS are classified into two main types: short-duration bursts lasting less than 2 seconds, thought to originate from the mergers of neutron stars, and long-duration bursts lasting several seconds to minutes, associated with the collapse of massive stars into black holes. These cataclysmic events release vast amounts of energy and are detectable across billions of light years, providing insights into the deaths of massive stars, the formation of black holes, and the conditions in the early universe. 57. The cosmic distance ladder is a series of methods astronomers use to measure distances to celestial objects, from nearby planets and stars to galaxies and clusters of galaxies. These methods include geometric techniques such as parallax for nearby stars, standard candles like Cepheid variables, and Typea supernovae for galaxies in the local universe, and cosmological distance indicators such as the redshift of galaxies for measuring cosmic distances on larger scales. The cosmic distance ladder enables astronomers to map the vast expanse of the universe, determine the scale of cosmic structures, and calibrate fundamental properties of the universe, such as its age and expansion rate. 58. The Lyman alpha forest is a series of absorption lines in the spectra of distant quasars caused by intervening clouds of neutral hydrogen gas in the early universe. These absorption lines appear as a forest of lines overlapping in quasar spectra, each corresponding to different redshifts and densities of hydrogen gas along the line of sight. Studying the Lyman alpha forest provides astronomers with a powerful tool to probe the distribution of matter in the universe at different cosmic epochs, revealing the structure and evolution of cosmic web filaments and the transition from neutral to ionized gas during the epoch of reionization. 59. Interferometry is a technique used in astronomy to combine signals from multiple telescopes to obtain a higher resolution and sensitivity than is possible with a single telescope. Radio interferometry, such as the Very Large Array VLA or the Event Horizon Telescope allows astronomers to achieve detailed images of celestial objects and phenomena by effectively creating a virtual telescope with a diameter equal to the maximum separation between the individual telescopes. Interferometric observations have been crucial in studying phenomena like black holes, pulsars, and the structure of galaxies across different wavelengths of light. 60. White dwarfs are remnants of stars like the Sun that have exhausted their nuclear fuel and shed their outer layers, leaving behind a dense core composed of electron-degenerate matter. These stellar remnants are roughly the size of Earth, but can have masses up to 1.4 times that of the Sun, known as the Chandrasekhar limit. White dwarfs gradually cool over billions of years, eventually fading into black dwarfs. They are essential for understanding stellar evolution, serving as endpoints for stars with initial masses up to 8 times that of the Sun and playing a role in phenomena such as Typea supernovae. 61. The cosmological principle is a foundational concept in cosmology stating that the universe, on large scales, is homogeneous, uniform, and isotropic, looks the same in all directions. This principle forms the basis of modern cosmological models, including the Big Bang Theory, and implies that the universe's properties are the same for all observers regardless of their location. Observations of the cosmic microwave background radiation and the large-scale distribution of galaxies support the cosmological principle, providing evidence for the uniformity and structure of the universe on vast scales. 62. Magnetars are a type of neutron star with extremely strong magnetic fields, up to 1,000 times stronger than those of typical neutron stars. These intense magnetic fields can exceed 1015 Gauss, leading to dramatic effects such as the emission of bursts of X-rays and gamma rays, occasional starquakes, and the generation of powerful magnetic storms in their surroundings. Magnetars are thought to form from the remnants of massive stars that undergo supernova explosions, collapsing into neutron stars with residual magnetic fields amplified by their rapid rotation. Studying magnetars provides insights into the behavior of matter under extreme magnetic fields and the physics of compact objects in the universe. 63. Extragalactic astronomy is the branch of astronomy concerned with the study of objects and phenomena outside the Milky Way galaxy. It encompasses the observation and analysis of galaxies, galaxy clusters, active galactic nuclei (AGNS), and other structures located beyond our own galactic neighborhood. Extragalactic astronomy provides insights into the formation, evolution, and large-scale distribution of galaxies, offering clues about the broader cosmic environment and the underlying processes driving cosmic structure and dynamics. 64. Dark energy is a mysterious form of energy that permeates all of space and is thought to be responsible for the accelerated expansion of the universe. First inferred from observations of distant supernovae in the late 1990s, dark energy constitutes approximately 68% of the total energy density of the universe. Unlike dark matter, which interacts gravitationally with ordinary matter, dark energy exerts a repulsive gravitational force that counteracts the attractive force of gravity, causing galaxies to accelerate away from each other over cosmic time. Understanding the nature of dark energy remains one of the most significant challenges in cosmology, with implications for the ultimate fate and structure of the universe. 65. Neutrinos are fundamental particles with extremely low mass and no electric charge, making them difficult to detect. Produced in various astrophysical processes, including nuclear reactions in stars, supernova explosions, and interactions with cosmic rays. Neutrinos offer unique insights into high-energy phenomena and conditions in the universe that are inaccessible to other forms of radiation. Neutrino observatories, such as IceCube in Antarctica, aim to detect neutrinos by observing the faint flashes of light produced when neutrinos interact with ice or water molecules, providing information about their origins and the astrophysical processes that produce them. 66. The Great Attractor is a gravitational anomaly located in the Centaurus supercluster, roughly 150 million light-years away from Earth. It exerts a significant gravitational pull on our Milky Way galaxy and countless other galaxies within the local group. The nature of the Great Attractor was first discovered through observations of galaxy motions in the 1970s and remains a subject of ongoing study. It is thought to be a massive concentration of dark matter and galaxies that influences the flow of galaxies in our local cosmic neighborhood, shaping the large-scale structure of the universe on scales exceeding hundreds of millions of light-years. 67. The Oort cloud is a hypothetical spherical cloud of icy objects that surrounds the Sun at a distance of roughly 2,000 to 200,000 astronomical units. Astronomical unit. It is believed to be the source of long-period comets that periodically enter the inner solar system from the outer reaches of the Sun's gravitational influence. Named after Dutch astronomer Jan Oort, who first proposed its existence in 1950, the Oort cloud remains largely unobserved due to its immense distance from Earth. Its existence is inferred from the orbits of comets and other observational evidence, providing insights into the early history and formation of the solar system. 68. The Drake equation, formulated by astronomer Frank Drake in 1961, aims to estimate the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. It considers factors such as the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, and other variables to provide a framework for discussing the likelihood of intelligent life beyond Earth. While the values for many of these factors remain uncertain, the Drake equation remains a foundational tool in astrobiology and the search for extraterrestrial intelligence (SETI), stimulating ongoing research and speculation about our place in the cosmos and the potential for contact with other civilizations. 69. The Andromeda Galaxy, also known as Messier 31 M31, is the nearest spiral galaxy to the Milky Way, located approximately 2.5 million light-years away in the constellation Andromeda. Spanning about 220,000 light-years across, Andromeda is slightly larger than our own galaxy and contains over 1 trillion stars. Astronomical observations indicate that Andromeda and the Milky Way are on a collision course, expected to merge in approximately 4.5 billion years due to their mutual gravitational attraction. This cosmic event will reshape both galaxies and provide insights into galaxy formation, stellar evolution, and the future of our local group of galaxies. 70. The Sun is a middle-aged star located at the center of our solar system, composed mainly of hydrogen and helium gas undergoing nuclear fusion to produce energy. It is approximately 4.6 billion years old and has an expected remaining lifespan of about 5 billion years before it transitions into a red giant phase, swelling in size and engulfing Mercury and Venus before shedding its outer layers to form a planetary nebula. Ultimately, the Sun will collapse into a white dwarf, gradually cooling over trillions of years. The study of the Sun, known as heliophysics, is essential for understanding solar activity, space weather, and its influence on Earth's climate and technological infrastructure. 71. Cosmic inflation is a theoretical concept in cosmology that proposes a rapid exponential expansion of the universe in the first fraction of a second after the Big Bang. Proposed in the 1980s to address certain problems in the Big Bang theory, inflationary models suggest that the universe underwent a phase of accelerated expansion driven by a hypothetical scalar field called the inflaton. This rapid expansion would have smoothed out irregularities in the early universe, providing a mechanism for the uniformity observed in the cosmic microwave background radiation and the large-scale structure of the universe today. Although direct evidence for cosmic inflation remains elusive, observations of the cosmic microwave background and large-scale structure provide strong support for its theoretical framework, making it a key component of modern cosmological models. 72. Neutron stars are incredibly dense remnants of massive stars that have undergone supernova explosions, leaving behind a core composed almost entirely of neutrons. These exotic stellar objects pack more mass than the Sun into a sphere roughly the size of a city, resulting in densities comparable to atomic nuclei. Neutron stars exhibit extraordinary physical properties, including intense gravitational fields, rapid rotation rates, and powerful magnetic fields. Some neutron stars, known as pulsars, emit beams of electromagnetic radiation that sweep across space like cosmic lighthouses, detectable as regular pulses due to their rotational spin. Studying neutron stars provides insights into extreme states of matter, the physics of nuclear interactions under extreme conditions, and the behavior of matter in the presence of intense gravitational forces. 73. The cosmic web is a large-scale structure of the universe composed of interconnected filaments of galaxies and voids that span vast distances across space. This intricate network forms through gravitational attraction, with galaxies and galaxy clusters congregating along dense filamentary structures while leaving expansive voids relatively devoid of galaxies. The cosmic web represents the large-scale distribution of matter in the universe and serves as a framework for understanding cosmic evolution, galaxy formation, and the growth of structures over cosmic time. Observational surveys mapping the cosmic web provide crucial insights into the underlying cosmic structure, the nature of dark matter and dark energy, and the processes shaping the evolution of galaxies and galaxy clusters within the cosmic landscape. 74. Gravitational lensing is a phenomenon predicted by Albert Einstein's general theory of relativity, where the gravitational field of a massive object, such as a galaxy or cluster of galaxies, bends and distorts light from more distant objects behind it. This effect can produce multiple images or distorted, magnified views of background galaxies, stars, or quasars, providing astronomers with a powerful tool to study both the foreground lensing object and the background source. Strong gravitational lensing can create Einstein rings, arcs, and multiple images of the same source, offering insights into the distribution of dark matter within the lensing object and enabling detailed investigations of distant galaxies and their properties. 75. The cosmic microwave background CMB radiation is the afterglow of the Big Bang, permeating the entire universe. It was first detected in 1965 by Arno Penzias and Robert Wilson and is now considered one of the strongest pieces of evidence supporting the Big Bang theory. The CMB radiation is extremely uniform, with small fluctuations providing crucial information about the early universe's conditions, including its age, composition, and expansion history. Detailed measurements of these fluctuations by missions such as the Planck satellite have allowed scientists to create precise maps of the CMB, revealing insights into the universe's evolution and the formation of galaxies and larger structures. 76. Magnetohydrodynamics (MHD) is a branch of astrophysics that studies the behavior of ionized gases plasmas in the presence of magnetic fields. MHD processes are essential for understanding various astrophysical phenomena, including star formation, solar flares, and the dynamics of accretion disks around black holes and neutron stars. Magnetic fields play a crucial role in shaping cosmic structures and influencing the behavior of plasma on scales ranging from individual stars to galaxy clusters. Computational simulations incorporating MHD principles help astronomers model and understand these complex phenomena observed throughout the universe. 77. Stellar nucleosynthesis is the process by which stars produce elements heavier than hydrogen and helium through nuclear fusion reactions in their cores. This process begins with the fusion of hydrogen into helium, which powers stars like our Sun. As stars evolve, they fuse helium into heavier elements such as carbon, oxygen, and eventually iron through successive stages of nucleosynthesis. Elements heavier than iron are predominantly formed in supernova explosions or during the merger of neutron stars. Stellar nucleosynthesis enriches the interstellar medium with elements crucial for the formation of planets, the origin of life, and the diversity of chemical compositions observed in stars and galaxies throughout the universe. 78. Exoplanets or extrasolar planets are planets that orbit stars outside our solar system. The discovery of exoplanets has revolutionized our understanding of planetary systems and their diversity. The first confirmed detection of an exoplanet orbiting a Sun-like star was made in 1995. And since then, thousands of exoplanets have been discovered using various detection methods, including the transit method detecting the slight dimming of a star as a planet passes in front of it. The radial velocity method detecting the star's wobble caused by the planet's gravitational pull, and direct imaging. Exoplanet studies provide insights into planetary formation, habitability conditions, and the prevalence of different types of planets in our galaxy. 79. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape from them. They are formed when massive stars undergo gravitational collapse at the end of their life cycle or through the merger of smaller black holes. Black holes come in different sizes, from stellar mass black holes with a few times the mass of our Sun to supermassive black holes found at the centers of galaxies with millions to billions of solar masses. Studying black holes provides insights into extreme gravity, the dynamics of galaxies, and the evolution of the universe on both cosmic and local scales. 80. Astrobiology is a multidisciplinary field that explores the origin, evolution, distribution, and future of life in the universe. It combines principles from astronomy, biology, chemistry, geology, and planetary science to study the conditions and potential for life beyond Earth. Astrobiologists investigate extreme environments on Earth that mimic conditions on other planets or moons, search for biosignatures in the atmospheres of exoplanets, and explore the potential for microbial life in our solar system and beyond. The search for extraterrestrial life is a central focus of astrobiology, aiming to address fundamental questions about life's cosmic significance and its potential diversity in the universe. 81. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. They originate from sources such as supernovae explosions, active galactic nuclei, and other energetic astrophysical processes. When cosmic rays collide with Earth's atmosphere, they produce secondary particles that can be detected at the surface, providing insights into their origins and the astrophysical processes that accelerate them to such high energies. Cosmic rays contribute to ionization in Earth's atmosphere and pose challenges to space missions and electronic equipment due to their penetrating nature. 82. The concept of gravitational waves was first proposed by Albert Einstein in 1916 as a prediction of his general theory of relativity. Gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects such as black holes and neutron stars orbiting each other or merging. These waves propagate outward at the speed of light and can be detected on Earth by sensitive instruments like the Laser Interferometer Gravitational Wave Observatory LIGO and Virgo. The direct detection of gravitational waves in 2015 confirmed a major prediction of Einstein's theory and opened a new era of gravitational wave astronomy, allowing scientists to study cosmic phenomena inaccessible by other means. 83. The interstellar medium ISM is the material that fills the space between stars in a galaxy. It consists of gas, mostly hydrogen and helium, dust grains, cosmic rays, and magnetic fields, which play crucial roles in the formation and evolution of stars and planetary systems. The ISM is divided into different phases, including dense molecular clouds where stars form, diffuse atomic gas, and ionized regions energized by hot stars. Observing the ISM in various wavelengths of light provides astronomers with valuable information about the physical conditions and processes shaping galaxies and their environments over cosmic timescales. 84. The habitable zone Goldilocks zone is the region around a star where conditions are favorable for liquid water to exist on a planet's surface, a crucial ingredient for life as we know it. The boundaries of the habitable zone depend on the star's luminosity and the planet's distance from the star, ensuring temperatures are neither too hot nor too cold for liquid water to be stable. Studying exoplanets within their stars' habitable zones is essential for identifying potential targets in the search for life beyond Earth and understanding the diversity of planetary systems in our galaxy. 85. The Kuiper Belt is a region of the solar system beyond the orbit of Neptune, extending from about 30 to 50 astronomical units from the Sun. It is home to a vast population of small icy bodies, including dwarf planets such as Pluto, Haumea, Makemake, and Eris, as well as countless smaller objects known as Kuiper Belt objects (KBOs). Studying the Kuiper Belt provides insights into the formation and evolution of the outer solar system, the origins of comets, and the dynamics of small bodies in the solar system's outskirts. 86. Dark matter is a mysterious form of matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. Dark matter constitutes approximately 27% of the total mass energy content of the universe, influencing the formation and evolution of galaxies and galaxy clusters through its gravitational pull. Despite its pervasive influence, the nature of dark matter remains unknown, with candidates including hypothetical particles such as weakly interacting massive particles (WIMPs) and axions. Understanding dark matter is essential for unraveling the universe's structure and the fundamental forces governing its evolution. 87. The Drake equation, formulated by astronomer Frank Drake in 1961, aims to estimate the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. It considers factors such as the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, and other variables to provide a framework for discussing the likelihood of intelligent life beyond Earth. While the values for many of these factors remain uncertain, the Drake equation remains a foundational tool in astrobiology and the search for extraterrestrial intelligence (SETI), stimulating ongoing research and speculation about our place in the cosmos and the potential for contact with other civilizations. 88. The heliosphere is a vast bubble of charged particles, plasma, and magnetic fields that surrounds our solar system, extending far beyond the orbit of Pluto. Created by the solar wind emanating from the Sun, the heliosphere acts as a protective shield that deflects most of the harmful cosmic rays and interstellar particles from entering our solar system. Understanding the heliosphere and its interactions with the interstellar medium is crucial for assessing space weather, protecting spacecraft and astronauts, and exploring the boundaries of our solar system with missions such as Voyager and New Horizons. 89. Quantum mechanics is a fundamental theory in physics that describes the behavior of particles at the smallest scales, such as atoms and subatomic particles. It provides a framework for understanding phenomena like particle-wave duality, uncertainty principle, and quantum entanglement. Quantum mechanics plays a crucial role in astrophysics, particularly in the study of compact objects like white dwarfs, neutron stars, and black holes, where extreme gravitational fields and quantum effects interact. Understanding quantum mechanics is essential for interpreting observational data and theoretical models in astrophysics, offering insights into the nature of matter and the fundamental forces governing the universe. 90. The Roche limit is the distance within which a celestial body, held together by its own gravity, will disintegrate due to tidal forces from a more massive body. Named after French astronomer Édouard Roche, who first calculated it in 1848, the Roche limit determines the minimum distance at which a moon or a planetary ring can exist around a planet without being torn apart by tidal forces. Understanding the Roche limit is crucial for studying the formation and stability of planetary rings and the dynamics of satellite systems in the solar system and beyond. 91. The cosmic microwave background CMB polarization is a measure of the orientation of polarized light in the CMB radiation. Polarization patterns in the CMB provide valuable information about the early universe's conditions, including the density of dark matter, the presence of gravitational waves from cosmic inflation, and the epoch of reionization. Observations of CMB polarization are conducted by sensitive instruments such as the Planck Light and ground-based telescopes, aiming to refine our understanding of cosmological models and the fundamental parameters that govern the universe's evolution. 92. The habitable's own Goldilocks zone around a star refers to the region where conditions are favorable for liquid water to exist on a planet's surface, a key ingredient for life as we know it. The boundaries of the habitable's zone depend on the star's luminosity and the planet's distance from the star, ensuring temperatures are neither too hot nor too cold for liquid water to be stable. Studying exoplanets within their stars' habitable zones is essential for identifying potential targets in the search for life beyond Earth and understanding the diversity of planetary systems in our galaxy. 93. The concept of time dilation, as predicted by Einstein's theory of relativity, states that time runs slower for objects moving relative to an observer compared to those at rest. This effect becomes significant at speeds approaching the speed of light and near massive gravitational fields. Time dilation has practical implications for GPS satellites, which must account for both special and general relativistic effects to maintain accurate time synchronization with Earth-based receivers. 94. The concept of a blackbody refers to an idealized object that absorbs all electromagnetic radiation incident upon it and emits radiation at a characteristic temperature-dependent spectrum. Stars, including the Sun, closely approximate blackbodies and emit radiation that can be approximated by Planck's law of blackbody radiation. Analysis of blackbody spectra provides insights into the temperatures, compositions, and evolutionary stages of stars and other celestial objects. 95. The concept of the Roche limit, named after Édouard Roche, is the distance within which a celestial body, held together by its own gravity, will disintegrate due to tidal forces from a more massive body. This limit determines the minimum distance at which a moon or a planetary ring can exist around a planet without being torn apart by tidal forces. Understanding the Roche limit is crucial for studying the formation and stability of planetary rings and the dynamics of satellite systems in the solar system and beyond. 96. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. They originate from sources such as supernovae explosions, active galactic nuclei, and other energetic astrophysical processes. When cosmic rays collide with Earth's atmosphere, they produce secondary particles that can be detected at the surface, providing insights into their origins and the astrophysical processes that accelerate them to such high energies. Cosmic rays contribute to ionization in Earth's atmosphere and pose challenges to space missions and electronic equipment due to their penetrating nature. 97. The Drake equation, formulated by astronomer Frank Drake in 1961, aims to estimate the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. It considers factors such as the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, and other variables to provide a framework for discussing the likelihood of intelligent life beyond Earth. While the values for many of these factors remain uncertain, the Drake equation remains a foundational tool in astrobiology and the search for extraterrestrial intelligence (SETI), stimulating ongoing research and speculation about our place in the cosmos and the potential for contact with other civilizations. 98. The concept of gravitational lensing is a phenomenon predicted by Albert Einstein's general theory of relativity, where the gravitational field of a massive object, such as a galaxy or cluster of galaxies, bends and distorts light from more distant objects behind it. This effect can produce multiple images or distorted, magnified views of background galaxies, stars, or quasars, providing astronomers with a powerful tool to study both the foreground lensing object and the background source. Strong gravitational lensing can create Einstein rings, arcs, and multiple images of the same source, offering insights into the distribution of dark matter within the lensing object and enabling detailed investigations of distant galaxies and their properties. 99. The concept of the heliosphere is a vast bubble of charged particles, plasma, and magnetic fields that surrounds our solar system, extending far beyond the orbit of Pluto. Created by the solar wind emanating from the sun, the heliosphere acts as a protective shield that deflects most of the harmful cosmic rays and interstellar particles from entering our solar system. Understanding the heliosphere and its interactions with the interstellar medium is crucial for assessing space weather, protecting spacecraft and astronauts, and exploring the boundaries of our solar system with missions such as Voyager and New Horizons 100. The concept of the cosmic microwave background CMB radiation is the afterglow of the Big Bang, permeating the entire universe. It was first detected in 1965 by Arno Penzias and Robert Wilson and is now considered one of the strongest pieces of evidence supporting the Big Bang theory. The CMB radiation is extremely uniform, with small fluctuations providing crucial information about the early universe's conditions, including its age, composition, and expansion history. Detailed measurements of these fluctuations by missions such as the Planck satellite have allowed scientists to create precise maps of the CMB, revealing insights into the universe's evolution and the formation of galaxies and larger structures. Exploring these 100 facts about astronomy has been a fascinating journey through the wonders of our universe, from the mysteries of black holes and dark matter to the intricacies of exoplanets and cosmic microwave background radiation. Each fact represents a glimpse into the vastness of space and the complex processes that shape our cosmic environment. Thank you for joining me on this exploration of astronomy and astrophysics. May these insights inspire further curiosity about the universe and our place within it. Goodbye for now.